Welcome to chapter 28. This is on the theory of special relativity. I know it seems odd to do this in the fall semester, but we have so many topics to cover in the spring that in order to fit everything in, special relativity sometimes gets grouped to the first part of the course. So we'll start with this. In order to understand some of the background, we need to talk about the fact that the way you observe things depends a lot on what is your reference frame. So if I'm standing by the side of the road and I see cars drive by, I have one reference frame. But if I'm in one of those cars, I have a different reference frame. We can go to another common example. The sun rises in the east and sets in the west. Well, you and I know that this earth is not stationary, that it is not the sun doing the moving, that it's the rotation of the earth that lets us believe that the sun is moving across the sky. Or maybe something a little more readily understandable, riding in a car. If you sit in a car and you look out the window when you're in the parking lot, the trees are sitting still. When the car begins to move, at some point in your ride, when your car reaches a cruising velocity, you're not speeding up, you're not slowing down, it's going to feel to you like you're stationary and the trees are the ones whizzing by the car. So all of that, our observations are dependent on our reference frame. And that leads us to, in physics, define a concept of an inertial reference frame. An inertial reference frame is a stationary reference frame or a reference frame that moves at a constant velocity. So it is a non-accelerating reference frame. In our little graphic, you see we have a person standing on the ground. They're in an Earth-based inertial reference frame. You're in the plane. If the plane is moving at a constant velocity, it's reached cruising velocity, then it is also an inertial reference frame. But there is no way something like the space shuttle, when it used to take off, could be an inertial reference frame at liftoff, because anytime you go from sitting still to traveling upward, you are accelerating. So, inertial reference frame, stationary or moving at a constant velocity. What is really neat about these is that all inertial reference frames are equally valid. So the laws of physics will hold in each of them. Once the airplane reaches a constant velocity, you could do a physics experiment there and get the same results that you might, excluding gravity interactions, so the same results that you might get on an experiment based in the lab. Alrighty. So Maxwell, whom we'll talk about way next semester, has a list of equations that are used to describe the speed of light. And in those equations, the speed of light is fixed at 3 × 10⁸ meters per second in a vacuum. In physics, little c, when it's related to optics, is the speed of light in a vacuum. So little c is the speed of light in a vacuum, 3 × 10⁸ meters per second. Newton thought that speed should vary with reference frame speeds, and it really took Einstein to pull all this together for us. So let's move along. The Michelson-Morley experiment is sort of a fundamental to all of this. So in the Michelson-Morley experiment, what they were American scientists, I believe they did their work in Chicago, but what they were doing is trying to measure the speed of light in the ether. At one point in time, it was assumed that the Earth was held in space in something called the ether. The concept of a vacuum was just a little hard to grasp, that there might be so few molecules out there between the planets that we would consider it a vacuum. So Michelson and Morley set out to measure the speed of the Earth with respect to the ether. And they did their experiment using something called an interferometer. It has a series of mirrors that take a light beam and split it up into two parts, send it down different paths, and then bring it back together. And so the thought was that if you went with the ether, you'd go faster in that direction, and against the ether, it would go slower in that direction, so that there would be differences in the speed. When you brought the light back together, these differences in speed would shift the light enough that you'd get constructive and destructive interference, and we would see light and dark bands, which we call fringes. And the way the bands would change would tell us something about the speed of light in the ether, or at least that was the hope. So let's look at this. Michelson and Morley did a really thorough job. So they had a light source, and it was positioned so that the light hit a half-silvered mirror. Half-silvered mirrors allow light to reflect off of it, but it also allows light to go through it. So you and I have seen a half-silvered mirror. If you've ever seen the kind of mirrors, there's a room in Rhine. As you come in the front door of Rhine, there's a classroom on the right-hand side, and it was used initially for education classes. And so there's one place where there's a little closet-sized room beside it, so people could sit in it and observe. And that room had a half-silvered mirror, so the people in the little closet room could look out, and the people in the main room would just see a regular mirror. You and I know about these mirrors from TV shows. So when the police take somebody in for interrogation, there's always a big mirror in the room, and that hides the fact that on the other side there are people who are looking through that half-silvered mirror at the interrogation. So those kinds of mirrors are half-silvered mirrors. So light will go through, but light will also bounce off. So what this light source, the light gets split into two parts. One part goes up, hits the mirror, goes through, goes to the telescope. The other one goes through, hits the mirror, bounces off, goes to the telescope. And what happens is, because you've got these one beam of light split into two, when they come back together, you create what are called fringes. So it's an interference pattern of bright and dark. Usually they're rings for this kind of thing, but they could be bands. Now, Michelson and Morley set all this up. Their interferometer was set up on a block of granite. So all of this is mounted on a block of granite, and the block of granite is actually in a pool of mercury. So the idea was they wanted to cut down on vibrations. They were in a city. They didn't want outside traffic or anything to mess up their little delicate experiment. So here's a photograph, but again, it's hard maybe to see the details. You can see the mirror here, and there's another one there, and again, the details are hard to see. And honestly, I don't know which one is Michelson and which one is Morley. Sorry. All right, so any shift in your fringe pattern that couldn't be attributed to path differences should be related to the speed of light going with or against that magical ether. And again, here is a drawing of it, but this one I liked it because you could see the fringe pattern. They've got a sodium source, so the light has this sort of orangey yellow color to it. And the fringes are these light and dark sort of bullseye patterns that you see. All right, so they did the experiment in every possible orientation at every conceivable time of year, and they never found a fringe shift. So their conclusion was that there was no ether, so there's no preferred reference frame. No preferred reference frame. Which was kind of a bummer, but not really. And this is just another drawing of an interferometer where we have the light source over here, and it comes and it hits the mirrors and gets split. And then it gets split going the other way, and then comes back together and goes to the telescope where they look for the fringes. This interferometer has other uses. Sometimes what we'll do is let the light travel through a gas, and you can measure the speed of light in the gas compared to the speed of light in a vacuum by the difference in the fringe patterns. Alrighty, so let's look at some of the postulates of the special theory of relativity. There's also a general theory of relativity, but it works for non-inertial reference frames and is a little complicated for us right now. So we'll stick with this one. So in 1905, Einstein proposed a theory to reconcile the contradictions between what Newton thought and the fact that light the speed of light didn't seem to vary with the speed of the reference frame. And he called his work the theory of special relativity because it's only for inertial reference frames. Remember, those are the ones that are sitting still or moving at a constant velocity. So his first postulate is the relativity principle, and it says that the laws of physics have the same form in all inertial reference frames. So that goes back to I ought to be able to do an experiment in a lab, an experiment in a plane, as long as the plane is moving at a constant velocity. The second postulate, called the constancy of the speed of light, says that light propagates or moves through empty space with a definite speed. Remember, we call the speed of light little c, independent of the speed of the source or observer. And in physics, when they say empty space, they mean a vacuum. All right, some of the outcomes of these postulates, there are all kinds of little thought experiments that can be done with this information. So one outcome is that simultaneity is not absolute. What the heck does that mean? That means that just because I say two events occurred simultaneously does not mean that a second observer will agree with me. And so to support this, we look at the famous really fast train. So you have a really fast train, and then you have an observer not on the train. So guy on the train, not on the train. Two identical lightning bolts strike two trees at exactly the same time. I know, because I'm standing here over on the ground and I see it all. Lightning bolt A, lightning bolt B, simultaneous, I say. But if you are on the train and you are traveling at relativistic speeds, what is a relativistic speed? A speed that approaches the speed of light. So 4/5, that'd be 0.8 times the speed of light is pretty darn fast. So if you're going that fast, you are going to see the lightning bolt hit tree B before you see the lightning bolt hit tree A because you are moving towards B. So just because the guy on the train says, no, they're not simultaneous, B happens before A. The guy on the ground says, no, they are simultaneous. A and B happen at the same time. Simultaneity is not absolute. It depends on your reference frame. So another thing, that's because we're not in inertial reference frames. Time dilation and the twin paradox are also related to this. So time dilation says that moving clocks run slow. Now, when we say run slow, it means that it takes less clock time to perform your task than real time. If your watch is running slow, instead of taking you 10 minutes to walk from your dorm to class, it might only take you 8 minutes. So let's look at a light clock to see how this works. So if we have a stationary light clock, light goes up, hits the mirror, comes back, ding, 1 second. So to calculate the time, we know that the speed of light is going to equal the distance traveled, so that's 2d up and back, divided by the change in time. So to figure out what is that change in time, well, it's 2D divided by C. Suppose we have the moving clock. We're out here observing from outside the whole time. So now we're outside, we have our clock on a rocket. So inside the rocket, you can pretend that this expanded view is what's going on inside the rocket. Inside the rocket, the light sends a beam to the stationary mirror, and then it comes back to the detector and bing, 1 second. So it takes 1 second to go from here to here, according to your light clock. But this distance is bigger than in the stationary position. So standing outside, you would say, gee, 1 second, but I only covered this little distance when the clock is sitting still, and I cover this bigger distance when the clock is moving. So the change in time is equal to the stationary time divided by the square root of 1 minus v squared over c squared. It's different. So the moving time is going to be greater than the stationary time. So you've got more time when you move at a relativistic speed, so you can get more done. Stationary time is sometimes called proper time or rest time in these examples. All right, let's see how that relates to time dilation and other things. So back in the early 1970s, they put atomic clocks, those are clocks that are very, very precise, into jets, and they flew in different directions really fast. And they found that depending on which way the clock moved, you either gained, you were 10 nanoseconds off or 7 nanoseconds off. I'm sorry, 59 nanoseconds off one way and 273 the other. Which was a significant difference. They've also done experiments in Europe at CERN, which is a research facility, that showed that subatomic particles called muons actually have different lifespans depending on whether they're moving or stationary. And again, relativistic speeds mean speeds approaching the speed of light. How does this get us to the twin paradox? So the twin paradox says you have two twins. Well, you have a set of twins, okay? Two brothers in this case. One twin stays home and the other goes off on a space adventure. And if we let 60 years elapse on Earth, then what happens is the space twin actually has 9.3 years more of life possible than the Earth twin does. So what they say, and let's see if we can get the paradox part of it. So what it all boils down to is a paradox, what they say about their experience. So the earthbound twin says, I stay still, you fly away, I'm the inertial reference frame. So you're younger than I am because your moving clock runs slow. The space twin says, no, I'm in my spaceship. Earth flew away from me. You're younger, I'm the correct age. And the paradox is they both can't be right. Well, the correct answer is the one in the inertial reference frame is right. The rocket is not an inertial reference frame. It accelerates as it flies away and comes back down. So it's the Earth twin that is in the inertial reference frame. And this is a pretty sorry little graphic, but it was better than nothing. All right, let's talk about length contraction. Let's get off the twin paradox. I never really liked it in the first place, but I like length contraction. So moving objects become shorter in the dimension of travel. And again, this is if you move at relativistic speeds. So speeds approaching the speed of light. We have an equation. It gives you moving length as a result of proper length and your speed. And I've got my little relativistic athlete. If my relativistic athlete runs to the right, if he runs in the x direction, he will become contracted in the x direction. So normally you run in a forward direction, so that would mean the distance between your belly button and your backside would shrink if you could run at relativistic speeds. Suppose you can jump at relativistic speeds and we put you in the y direction. So if we're going, like in the drawing, instead of running, we're going to have him jump at relativistic speeds. So if you can jump at relativistic speeds, that means whatever motion in that direction you take, you'll be reduced in that direction. So he's actually going to be shorter. The distance between his head and the soles of his feet would be reduced. And then lastly, suppose we let him, he's really good at this moving sideways. There are exercises for that. I guess it helps with agility. Anyhow, he's going to be moving sideways, so in the Z direction, in and out of the paper. And if he moves, oops, the way I've got him pointed, to the right would be sideways, and in and out of the paper would be belly button to backside. So you change in the direction of motion. I guess that's the takeaway with all of that. And you shrink. Jump up and you're shorter. Move to the right and then the distance between your left side and your right side is smaller. Come out of the page towards us, distance between belly button and backside is smaller. All right, enough of that. Four-dimensional space-time. So 3 dimensions, X, Y, Z, up, down, right, left, in, out. The 4th dimension is time. To really pinpoint an event, you have to know not only where did it take place, but when did it take place. And then another thing with the relativistic speeds, if you move at relativistic speeds, moving objects have an increase in mass. And again, you have an equation for it. If you look closely at the equation, v squared over c squared is in the denominator. You take 1 and subtract that from it. Because it's in the denominator and we're taking the square root of it, we can't have the number inside the square root be a negative number, because the square root of a negative number is an imaginary number. We don't want that. So objects can't go faster than the speed of light. We used to think of the speed of light as sort of the speed limit. But now we believe that objects that start out slower than the speed of light can't go faster, but that there are some objects that start out faster. We believe there are some objects, again, these are subatomic particles. We think they do start out faster. So moving objects show an increase in mass. And then finally, energy and mass. So this is Einstein's famous equation, E equals mc squared. E is the energy measured in joules, m is the mass in kilograms, and c squared is the square of the speed of light, which would be 3 times 10 to the 8 meters per second, and then you'd square it. So you get a big number. And that is all we're going to say about relativity.